yeah, I'm going to be giving an introduction to RISC-V. I was originally giving a talk on eBPF, but then I was more motivated to do this because I have currently found that I have a lot of time on my hands being unemployed. So I've been playing around with a lot of hardware, and this seems super cool. And there's like a Go aspect to it, so just bear with me. So what is RISC-V? So it's a new instruction set architecture. So in order to kind of explain RISC-V, I'm gonna explain what instruction set architectures are. So what is that? Which was the next question. So it's the interface between the software and the hardware. It's really the interconnect between the two. And then assembly language comes on top. So it's the pseudo instructions on top of the ISA, which is the instruction set architecture. So the one that most people seem to be familiar with is x86. And this is one of my favorite Twitter accounts, and I'm kind of mad that I didn't think of it myself, to be honest. So they take the abbreviations of the x86 instructions and then they just make up things for them. So this one's automatically do the slightly wrong thing, which is probably an actual instruction based on the behavior of x86. So the other kind of interesting thing about x86 is that no one really knows exactly how many instructions there are. If you get an Intel x86 manual these days, it's this big, 5,000 pages. So it's really unwieldy to deal with, which is kind of where RISC-V comes in. But first, let's go over some of the differentiating factors of instruction sets. So different processors can implement the same exact instruction set. So you can have AMD and Intel both implementing x86, and then ARM will implement ARM and stuff like that. So it's kind of just that interface that you can use, which is cool. And then depending on the vendor, you're going to get a different size. It will cost a different amount of money, blah, blah, blah. So the way that you kind of define the different architectures are based on the complexity of the instruction set. So RISC is cool because it's reduced. It's a minimal interface. It only implements what you would have most of your programs using, and then for everything else that's kind of complex, it will use a subroutine, and that has a trade-off with performance, but it's those things that you really aren't using and your program might not even need. And then there's the complex instruction sets, and these are super specific. They have instructions for literally everything. Release the bees is complex. They combine a bunch of different instructions into one, and then they also have the factor of doing memory access and then computation in the same instruction, which is a differentiating factor of a complex instruction set versus reduced. So these are kind of the two main ones, and these names weren't even made up until long after computers existed. So if you try to figure out which computer is which one, they're well, maybe it was RISC or maybe it was not. So it's not these terms really define exactly what it is. So going back into even more super obscure instruction sets, we have the very long instruction word, and then EPIC, which is very similar, and these run instructions in parallel. So contrary to the two others that we talked about, those will run one instruction, one instruction, one instruction, one instruction, and these will do them in parallel, which is cool, but it leaves a lot of the kind of logic and stuff like that to the compiler versus the hardware, which is also super awesome in a way. It really depends on what trade-off you need. Everything in computing, it depends on the trade-off. So then there are these two kind of super obscure ones that if you look them up, they haven't really been commercialized or anything like that, but they're kind of interesting just for the sake of telling you about them, and I thought it was cool. So there's minimal instruction set computer, and this is super, super small. It has to be anywhere between 32 instructions, which if we go back to x86 has somewhere around like 2500, there's this whole talk where this guy tries to reverse engineer like how many instructions there are, and I'm sure that there's like an instruction that's like send data to the NSA or whatever. So this one has 32, which is cool. You can like probably audit them way better. Like it will have anywhere between 1 and 32, but if you have 1, then it's called the 1 instruction set computer, and that's only like 1 instruction. So like this instruction needs to be like Turing complete, which move is Turing complete. There's like this whole paper on it if you want to read it. And then there's like a bunch of other instructions that you can use, like 5 different subtractive instructions that will work for this, which is really cool. So like the 1 instruction set computer, like you're most likely going to hear about in some sort of like computer science class where they're kind of showing you how to build instructions on other instructions and stuff like that. But it's still interesting. I mean, if you find this interesting, I did enough to tell you about it, so here we are. So one of the things I like really wanted to dive into is like, why did they do this? Like, why did they make a new instruction set? Like here we are in, 2018, they did this like a few years prior though, and it's just like, why are we still coming up with instruction sets? Like why? What did we fuck up so bad that we need a new one, right? And it turns out like a lot. We kind of fucked up a lot, and moving into more modern eras, we need different sets of things. So one of the main things that they really wanted to get with RISC-V was like a free and open instruction set architecture. And like this is what I really love about this, because when you look at kind of the way that computing in general is moving, like everything seems to be like open source. There's even a whole ecosystem nowadays of like open source firmware, which I'll get into a bit later on in this talk. But if we can have almost open source all the way down the stack in computing, it's like we have gotten rid of all the proprietary software, and we have like a fully auditable stack from the bottom up, and that is like super cool. So even having the open instruction set is awesome. And another like kind of design decision that they made that I really like is the extensions. So like they start with like a super minimal base of instructions, and then you can add on extensions and make your own custom extensions. So it's like fully extendable to whatever vendors want to add whatever crazy ass instructions that their hardware needs, right? So that's super cool. And then if you really want to get into like the nitty gritty here, there's this awesome paper on the design of the RISC architecture, and they go over like literally everything back to like the PDPs and like why that instruction set was bad. Like they really get into the details and like nail every single prior instruction set and say this is why we hate it. And I loved like that part of it because it was like, tell me what's wrong and how we messed up, and then go back and fix all the problems, which is what this whole paper outlines, and it's great. So kind of just to like give you a slight summary, although I can't like do it justice. Obviously, x86 is like way too complex, like 2,500 instructions. Like we don't even know if it's 2,500. It could be like way more than that. That was just like the last time someone, buzzed it. So ARM is like not open as well, but also it's still too complex. Like they have around 600 instructions, and that's just like unwieldy too. It's like, how can everyone keep track of all these instructions, right? Spark is actually kind of cool because when it was under Sun Microsystems, it was an open instruction set, which like props to Sun for doing that because that's super amazing. But then after they got bought by Oracle, Oracle kind of shut it down. So all the modern versions of Spark are like, closed off and have a different licensing model. So you can't use the open version of Spark and have it be open, which, like the modern version, and have it be open, and they added like new things that you need for modern computing. So yeah, if you want to like dive into a bunch of others, definitely check out the paper. So there's like a ton of problems that I've like noticed and just heard about from people that I've asked about proprietary firmware. Like I've seen them myself as well. Like you'll have a bug in your firmware and like you don't know if it's like a bug in your software or it's a bug in the firmware, and you're just like, I know it's not me, like I feel like I checked all my bases, but there is no source for the firmware, so you have no fucking clue other than the fact that like I am like 99% sure it's not me, but like that 1% is like, maybe. So then you like call up the vendor on the phone and you're like, well, I got this bug. And then they're like, no, you're fucking crazy. So it would be like really nice if there was like a definitive way to be like, no, that's you. I see your code right there or whatever. Then there's like a bunch of like unneeded complexity in proprietary firmware. Like if you look up how, the Intel management engine works and, all this stuff, like they have a like basic like tools in there that like you would never need, like runtime services. There is like SMM, like updating is actually good. Like we should keep that part, but we should have like auto updating. Like there's whole parts of this firmware that you could just throw in the trash, and it's just features that vendors add that like literally no one wants. And it adds more complexity, it adds more bugs. Like these firmware teams, like inside these companies, they don't even talk to each other. Because I was talking to like a firmware hacker, and they were like, yeah, sometimes when I find bugs, they're like, can you tell that team to do that? And it's like, at the same company, like the hacker is the one having to be the middleman in the communication. Like that's not great. So super bad. Running like any sort of server at scale with proprietary firmware is like super hard because of the problem that I said with like you don't know if the bug is you or the firmware. If you turn on like correctable errors, like sometimes things will just shut down and you're like, what happened? And then you don't know. So a lot of this is just like crazy logic that we don't know what's happening in the computer, and when anything goes wrong and you've checked all your bases, you just want to be like, it's the firmware. So not transparent, it's bad, it's terrible. That's my whole spiel. So like right now, what's kind of cool is there's like this whole like open source firmware movement, and they have like a bunch of cool stuff that they're working on. And since like Intel and ARM and like all the major chip providers still have proprietary firmware, they wrap this like binary blob that provides all the chip vendor stuff. And at first it was like this defined interface, and now it seems like all the vendors are just like shoving in more logic, and it's like, just stop doing that. Can you just like boot? That's all anyone cares about. Or just like let us handle the boot even. But it is still cool that there is like a bunch of tooling around open source firmware. But with like RISC-V, like we don't have to deal with like that proprietary vendor bullshit. Like you can actually build the firmware like from the base yourself, which is awesome. So Mirage OS unikernels, they have been working on using like running this on the bare metal as firmware. Like that's actually super freaking cool, because like unikernels, you get this like super minimal abstraction, and you're building custom kernels just for what you need. So the like firmware is kind of like the perfect use case for unikernels. So that's like super awesome to see. Then as far as like the Linux ecosystem, you have like Core Boot and Linux Boot. Linux Boot like uses Linux versus UEFI for booting, which is really cool. Core Boot was like the OG, open source firmware. And then there's U-Boot and UBMC, which are both written in Go from Google, and that's like super cool. U-Boot uses gRPC to do communication, which is cool. Or UBMC does that. And then there's OpenBMC, which is a project that's written in like 3 different languages. So I kind of prefer the Go one. So yeah, that's kind of like the state of open source firmware, and it's really cool to see that Go has a space there for doing things. So the state of Go on RISC-V, though, is a whole different story. And so I got like this board called the Hi5 Unleashed, and it runs Linux. That's like why I got that one. It's super cool. But then I was like, oh, I want to run a Go binary because like, Go's my language. So I like went to go see what the status is. And I know that they had like saved the keywords like RISC-V. But there's this issue on GitHub if you want to check it out. And T. Clauser, he's been doing like a shit ton of work and is super awesome, and been like carrying a lot of this. But it's kind of in a disarray. So this repo works. It's under RISC-V, but the problem is this repo is like, as you can see, quite old. So it's on a very old version of Go. So then I was like, oh, I'm gonna update it to like the latest. Like, no. There have been a lot of changes in the compiler. So that didn't work. This guy, T. Clauser, like he's working on it, but there's just been so many changes that it doesn't compile. But you can use, of course, the thing from a few years ago. So then I was like asking on Twitter, I'm like, oh, I'm trying to compile this thing. And so one of the people on the compiler team was like, oh, sorry, like we changed some stuff in the compiler. And I was like, oh yeah, like no shit, like it totally does not work. So it would be really nice if this could be figured out. And I've been like trying to look into it, but it's also like, I do not have the context of the entire Go compiler, and I don't have the context of like everything else that's been going on with the changes, so, or the original patches. So I'd have to like get both contexts. So it would be nice if someone who had at least one context could maybe help. So it is cool that you can like, you know, use it with the old version of Go, and I would show a demo of that, but since Linux on the desktop has failed me today, I'm very sad about it. You'll have to believe me. So, or you can find me after, and I'll show you just on my laptop. So also the future of like RISC-V or just like anything, what's cool is like you can also use like Rust to just like boot on bare metal into RISC-V because Rust I started looking into, they have this thing called libcore, and so you don't actually need like an OS layer to run like on the bare metal, which is like super cool, and that's kind of how TinyGo is. So you can do like embedded Go. So it would be cool if TinyGo also got support for RISC-V. That is basically what I wanted to say. You can find me after if you have questions, but I would love to see like any of these things happen, and I think it would be like great for, you know, the future of open source instruction sets and also open source firmware.